Hello and welcome everyone to EC3030. So in this video lecture we will be talking about noise in logic circuits. Now previously we have seen noise in the context of inverters. So in this lecture we will try to look at the origin of this noise that we talked about when we were discussing about noise margins in inverter. So first of all, just a quick recap of what we talked about in inverter regarding noise and noise margin. So essentially what we said was that an inverter is immune to noise to a certain extent, and that is essentially measured by the noise margins, the noise margin low and the noise margin high. Now what we're going to talk about in this lecture is the origin of the noise. So there are many origins of noise in a logic circuit. So we will consider only two of them. So the first one is what we call the crosstalk between the wires, and secondly the variation in the power supply voltage and the ground voltage due to the resistance and the inductance of the wires. All right. So now first the crosstalk. Now the crosstalk is essentially happening because of capacitive coupling between the wires. So to understand what we mean by capacitive coupling, let's look into the same interconnect analysis of the interconnects that we did in one of the previous lectures. So for example, if we think about any of these metal layers here, so say this is the metal layer that we are considering. So say this is what we call M2 here, and say this is M3 here, and say this is the M1 here. So essentially what happens is that in between this, for example, this metal layer and this metal layer, this is this oxide, and this represent this oxide capacitance here. Similarly, the capacitance between this wire and this wire is given by this capacitor here, and similarly this capacitance is given by the coupling capacitance occurs between these two lines here, and this capacitance occurs between this layer and this layer. So essentially there are a bunch of capacitors there, and these wires, the adjacent wires in the same metal layer or the metal layers above and below it, they are not coupled directly by uh, conductance, meaning that they are not, there is no short between them, but what happens is that there is a capacitance between them, and this capacitance causes a crosstalk between them. Now what does crosstalk mean? Crosstalk means that, say for example, this line is feeding to one inverter and this line over here is feeding to a completely different inverter. Essentially what it means that the signal in this wire will be completely uncorrelated with this, the signals that is going through this wire over here. But what will happen because of this capacitive coupling is that the signals in this wire will induce, so the voltages in this wire over here will induce some variation of the voltage that occurs here. Now again, the signal in this wire is supposed to be completely uncorrelated with this one, but then because there is some signal coming here going zeros and ones, this will induce some voltage variation here, and that effect essentially causes a noise in the signal that is carried by this wire over here. So to look at it more precisely, we can construct this kind of equivalent circuit, and let's say this is our line B, and say this is our, let's say this is our line B, and say this is our line A. Now between line A and B there is this capacitance which we called CWW. So the WW stands for capacitance between wire to wire capacitance. And let's say there is another capacitance, and that capacitance is basically from here to the ground, and that is called the CWG, basically wire to ground capacitance, the capacitance between this line over here and the semiconductor. So this is CW. So this is a very simple representation, and what we want to see is how the change in the voltage at the line A causes a change in the voltage line B. So if we just do a simple capacitive analysis, let's say the amount of charge here is plus Q on this plate and this is minus Q, and again the charge here is plus Q minus Q. Alright, so we can just say that VA minus VB is CWW multiplied with Q, and then we can say VB equals CW, sorry, this should have been Q over CWW, and VB is simply Q over CW dash G. Okay, so now if we just take the ratio between them, VA minus VB over VB will be equal to CW dash G over CWW, and then if we just simply do a little bit of more algebra, this is what we will get: CWW plus CWG over CWW. So essentially VB over VA is CWW over CWW plus CW dash G. So this is the equation, so let me write it over here again. So VB equals VA CWW over CWW plus CWG. Alright, so what it essentially means is that any voltage in this line will create a voltage in this line B, and the ratio of these two voltages is given by this fraction. Now what we want to have is that what we want to have, so essentially we can also write it like this: dVB over dVA equals CWW over CWW plus CWG. So essentially a change in VA will cause a change in VB, and ideally what we want is this ratio to be 0, so that a change in VA won't cause a change in VB. But achieving that is very difficult, and the reason is that CWW, the capacitance between metal lines, adjacent metal lines, is much larger than the capacitance between the line and the ground. And the reason is very simple. The reason is that the gap between metal lines that are adjacent are much shorter than the gap between the line and the ground. Essentially CWW is much larger than CWG. So as a result, this problem of crosstalk is actually pretty big. So there are different techniques that are applied to mitigate this crosstalk due to the capacitive coupling. One way of mitigating is to interleave the signals between the lines, the metal lines that carry signals, by ground planes. So for example, say you have 3 metal layers say you have 6 metal layers. This is the cross section. So say this is your metal A. Now rather than putting a second signal carrying line just next to it, you will put it slightly away like this, and this in between you will put a ground line. So in that way you will be able to reduce the crosstalk between A and B. And similarly, say you have a ground plane here and another signal carrying line C over here. So this way, by interleaving ground and the signal lines, you can mitigate the crosstalk to some extent. Another way is to twizzle the signals, meaning that you don't put two signal carrying metal lines to the same signal carrying metal lines adjacent to each other for an extended amount of length. What you do is, for example, say signal 1, signal 2 and signal 3 are adjacent for this amount of length. Then you then you connect it such that signal 1 is no longer adjacent to signal 2, rather it's adjacent to signal 3. And again, after some length, you again twizzle it such that signal 1 it changes its position with respect to signal 2 and signal 3. And as a result, what you do is you mitigate the effect of crosstalk to some extent in this way as well. And the other techniques are to use low dielectric constant interlayer dielectrics, ILDs, and use air gaps. So now these last 2 points is actually something that we have seen in one of the previous lectures when we were talking about how to reduce the delay in the interconnects. So the same techniques are used to mitigate the crosstalk effects. So just to show you here the air gap technology. So essentially air gap is the ultimate form of reducing the dielectric constant in the back end. So for example, here I'm showing it's a cross section of a 22 nanometer process which does not have any air gaps. But moving forward to 14 nanometer process, you can see in this zoomed out image that between these metal lines there are some air gaps that are introduced, and essentially what this metal air gap it does is that it reduces the dielectric constant between these metal lines and these metal lines from 4 for a silicon dioxide to 1 for close to 1 for an air gap. Alright, so now let's look at the second origin of noise, and that occurs because of the variation of the power supply voltage and the ground voltage. Now let's try to understand why there can be a variation of the power supply voltage and the ground voltage. The reason is essentially this, that say this is the power supply voltage. Now through the power distribution network, the same power supply voltage feeds a lot of the gates. For example, in this case, the inverters. So the same power voltage supply actually acts as the power supply for a lot of different gates. Now let's say this inverter is close to the power supply, but for this inverter is far away. So as a result, what will happen is that although these metal lines have a small resistance, because of the extended length, this will have a sizable amount of resistance. So as a result, what you can say is that there is a resistance in this wire, and so the power supply line and the ground line. There is a similar resistance for this inverter here from the power supply voltage to this inverter, but because the length is small, the resistance of these two lines over here is much smaller than the resistance of the line that carries power from the power supply voltage to the inverter that is further away. And essentially what will happen is that for this inverter, the power supply voltage will be smaller than VDD by an amount, say I is the current that is flowing in this direction, and for the ground line this direction. So the drop across this resistance will be IR, say this is IR supply, and this is IRG. So RG is the resistance of the ground line and RS is the resistance of the supply line. So essentially the voltage across this inverter, rather than being VDD, will actually be VDD minus IRS minus IRG. So essentially what will happen is that this inverter will see a smaller voltage than VDD. Okay. So let's do a quick calculation. Let's say the resistance per unit length is 0.44 ohm per micron. So resistance per unit length. And let's say this inverter draws a current of 150 microamps and the length of the wire is around 1500 microns. And 1500 micron is kind of long, but for the sake of it, let's say that it's this much. So then the voltage drop that will occur in this wire alone will be current multiplied with resistance per unit length multiplied with the resistance, and it will come out to be around 0.1 volts. Now 0.1 volts is a fairly large amount of voltage drop because the power supply voltage in today's microprocessors are around 1 volt or 0.8 volts, and if out of 0.8 volts 0.1 volt is lost, which is more than 10%, then essentially the logic block will see a voltage of say 1 volt minus 0.1 volt equal to 0.9 volts. So this is a significant issue. Now let's see how it affects the circuit operation for say an inverter. All right. So now let's say, again, let's consider this inverter case over here, and let's say there is a resistance of this line that is given by RG. All right. And what is interesting in this case is that the output of the farther away inverter feeds to the input of the inverter that is closer to the VDD. All right. So now what will happen is that the voltage, say we have the ground line has a resistance of RG, and for the sake of simplicities, let's say the supply line doesn't have a resistance. Supply line is wide enough such that its resistance is much smaller compared to that of the ground line over here. And let's say current that is flowing through this line is I over here, and the same I is returning this way. So as a result, the voltage drop across this resistance is IRG. Okay. So now, because there is no resistance, the voltage at this node will be VDD. On the other hand, at this node, the voltage, rather than being 0, will be IRG. Alright. So now, how will the voltage transfer characteristics for this inverter look like? Okay. So first, if the input is 0, then it's fine. The output will be VDD. But if the input is equal to VDD, then the output, so this pull down transistor will be on, and as a result this voltage will appear at V output. Now when the IRG is, when the RG is 0, this voltage will be 0 when the input is VDD. But if this voltage becomes IRG due to this drop in the ground line, this output voltage, rather than being 0, will become IRG, and as a result the inverter characteristics will look like this, meaning that when the input is VDD, the output, rather than being 0, will become IRG. Alright, so now think about what will happen. This output feeds to the input of this inverter. Now this inverter, because it's closer to the power supply voltage, doesn't have any resistance in the source or the drain. And essentially what will happen is that as it feeds this output, when it's supposed to feed a 0 voltage, it will actually feed a voltage which is equal to IRG. And this is how an input, this is one of the ways an input, rather than being 0, becomes larger than 0. So this is one origin of noise in the power supply voltage, noise in the inverter. Alright, and essentially the fact that the output of this inverter is not 0, rather a certain positive value, is actually called the ground bounce phenomena, because the ground, rather than being at 0, is at a non-zero value, and this is called the ground bounce phenomena. There are many other phenomena as well. For example, if the dominant resistance is in the source line, then the input, when the input is 0, the output, rather than VDD, will be smaller than VDD. So there are other kinds of effects also that can occur because of the line resistance. Alright, so how do we nullify the effect of such resistance occurring either in the source or the drain? Now what essentially happens is that the logic blocks, so usually ground bounce happens when a lot of the gates in a logic block are active at the same time, meaning that they're switching at the same time, and this is actually when this ground bounce phenomena happens, meaning that a lot of current starts flowing in and out of this logic block through the source line and the ground line. Now the way to nullify or mitigate the effect of this ground bounce is to add a capacitor parallel to the logic block between the ground and the source. Now what it does is that it stores some charge in usual time, and when the activity of the logic block is high, then rather than getting this current from this line over here, it will rather take the charge directly from the decoupling capacitor. Now note that this decoupling capacitor is right next to the logic block, so this extra amount of current that needs to flow does not flow directly from the source, rather it flows directly from the capacitor, and in doing so it mitigates the drop through a drop of the power supply voltage across this logic block during the high activity region, during the instances when the logic block goes through an high activity time duration. All right. Now when this high activity time duration is over, then again this capacitor gets charged through the voltage source. As a result, the voltage drop across the line can be nullified when the logic block goes through high activity durations. So let me give you a quick example. So let's say the maximum voltage change in the voltage that can be tolerated is delta V, and let's say in the logic block there are n gates meaning that logic gates, and each logic gate draws a current of I max for a time duration of T max. So the maximum amount of charge that this logic block will require during this time segment of high activity T max is N I max T max. So the decoupling capacitor needs to be, so Q max is CD delta V. So as a result, the CD should be N I max T max over delta V. So let's say the power supply voltage is 1 volt and the maximum voltage droop that you can sustain is 0.1 volts. You have 10 logic gates and the maximum activity period is 1 picosecond, and the maximum current that the transistor draws is 100 microamps. So based on this equation, the decoupling capacitor that I need to use is designed to be 15 femtofarads. Right. So another source of this fluctuation of the power supply voltage is the inductance. Now inductance, and the inductance usually is the highest at the pins, input output pins of the microprocessor chip or the package. So if you have an inductance and there is a sudden change in the current due to a high activity of the microprocessor or certain logic blocks, a voltage will develop at the pin that is given by VL equals L di dt. Alright, so let's look at an example of the inductance of pin. So in this example we will consider a Intel Xeon processor which came out in 2015. It has a total around 1500 pins, and out of this 1500 pins around 381 are for the power and 471 for ground. Okay, so each of the pin has approximately an inductance of half a nanohenry, and say the current in each pin for some reason changed by 100 milliamps within a time period of 10 nanoseconds, meaning that at time t equals to 0 the current was 0 through that ground pin, and at 10 nanosecond the current rose to 0.1 amps or 100 milliamps. So the rate of change of current is 0.1 over 10 nanoseconds, which is 10 power 7 ampere per second. So the voltage drop due to the inductance of the pin VL, which is equal to L di dt, is around 5 millivolts. Alright, so now let's consider the worst possible scenario where all the current in all of the 471 ground pins changed by 0.1 amps in 10 nanoseconds, and in that case each of the pins will develop a voltage of 5 millivolts across them. Now think about the case. So we talked about the worst case scenario where all the ground pins, the current changed by 0.1 amps in 10 nanoseconds. So essentially overall the total amount of current that rose is around 471 pins. Each pin the current changed by 1 ampere in 10 nanoseconds. So in total the total current changed by 47 amps within 10 nanoseconds. Now 47 amps is a huge number. It may not be realistic, but for the sake of simplicity, let's assume that the total amount of current that this microprocessor, the total amount of current that change in all the ground pins is 47 amps within 10 nanoseconds. Now think about the case, say you did not have 471 ground pins, just instead of 471 pins, you had one pin, and in this one pin the current changed by 47 amps in 10 nanoseconds. And then if you can calculate the L di dt, so your L is half a nanohenry, and the rate of change of current will be 47 divided by 10 nanoseconds, which gives you this number. And then essentially you will see that the total change in the voltage just due to the pin inductance would have been 2.3 volts. Now note that the microprocessor works at around 1 volt, so if that much of current change occurred, then theoretically you would have gotten a voltage drop of 2.3 volts, which would not have definitely happened because the power supply voltage would definitely drooped significantly. But anyway, that essentially shows as to why we have multiple many pins that support the ground signal and many pins that support the power signal in a microprocessor.